Alrighty, episode 10. Hard to believe. The last few episodes have just flew for me. Zero stress. Been able to get them out, which is great, and probably, hopefully, on your side, a lot less and on, which I do a lot of. As I said before, it's the videos are not rehearsed; they're done live. I pick a topic, I pick the parts off the shelves, do whatever I have to do in terms of research, or not research, but CAD. In this case, there was a lot of CAD, or a good bit of CAD. Think back to what I would need to say, think back of all the parts, why I need to say it, why it's important, what's different now, what happened in between, how to get that information across, and so this is where we're at now, thankfully. So yeah, episode 10. So I get a lot of people asking what has changed between this is what I call the Brian Hart, the very early engine, and the more modern engines. Now, the one thing I will need to say, I won't ever be covering the new, what would I call it, the V6 engines, because in my mind, and I think in everyone's mind, they're not engines, they're power plants. They've got a lot going on in terms of the engine to start with, generators, regenerative stuff. They're not, in my mind, a purist naturally aspirated engine, so I won't ever be covering those. If I got one in the morning for free, I don't think I'd do anything with it. They're just not exciting. Now, obviously, for the newer Formula One people, they might be, think they're brilliant, and the drivers are go around like soccer players. But I just don't. I don't buy it. I don't watch it. I never really watched Formula One, to be honest with you. I'm just more into the engineering of what they could bring materials to the maximum, the various casting technologies, coating technologies, pneumatic valve train. Even the aero now, it's ridiculous. Like sometimes I look there on Twitter, um, and I can't get excited about a tiny, whatever you call it, Reynolds number change in an aileron on a panel that has got 45 ailerons mounted to it in carbon fiber, and they went with a different paint which is more slippier. It's just ridiculous. So I don't follow modern Formula One at all. I'm more of an old school guy. I stopped watching it when, I don't know, probably after the last V8's finished, and it's just been downhill from there, in my opinion, in terms of engineering. Now, if you're into, if you're aerospace and you're into aerodynamics, that's brilliant, great. I know there's trade-offs there. You need power trade-offs with efficient aero, with efficient intercoolers, with efficient floors, with efficient planks, with efficient whatever vortices over the front wheels, and I just not into it. It's not my cup of tea. It's engineering, absolutely, but I can't get excited about a change in a chord shape of an aero profile on a wing. I just can't. So they'll never be covered on this channel. It'll always be this, always. Hopefully there'll be. I mean, there's so much to cover. The last Cosworth CA engine, or the last Ferrari engine. There's so much to cover in terms of the best engines. Even the road car I drive now, which I had a conversation with one guy, which was commenting on the channels. It's the last inline six BMW, and after that, I think they went to turbos. I mean, I don't even know what they went to. I think they went to either an inline six turbo or a inline four, something ridiculous. Like all the proper old school stuff is gone. So I'm not saying I'm old. I'm not old. I'm fairly young. I'm only 40, but it's just not my boat, I'm afraid. Now, I'm guessing there's all new technologies inside the engine. I think the rev to, is it 15,500 revs, which is not really stretching anything in my imagination. Maybe it is, but like these are light years ahead in terms of design and in terms of, engineering aspects. If you're an engineer, this is, I think, more up your street rather than the new stuff, which is like borderline EV sort of thing, which I won't be part of. Anyways, so in this episode, I haven't decided what to call it yet because it's going to be so wide range, I guess you'd call it. But what I probably will call it, or what it's probably going to be about, is advances in combustion chamber roof casting design. So I know that's a mouthful, but that's what this channel is about. That's where we are. So in the early engines, as you've seen before in the previous videos, again, this is the Brian Hart cylinder head coolant gallery, which is the only one I've been brave enough to cut up because the rest of them are too expensive. You've seen this before in the other videos. If you haven't, go back. I'll link it down so you can get up to speed on what's going on here. These are new, obviously. This is new. All these are new. We'll talk about them in a moment. But in the older engines, the big problem they had was the combustion chamber. Now, not the shape of the chamber itself, but the area over that where the coolant runs, where the spark plug sits, and where the valves sit. Now, I've been casting for a very, very long time. As I said on one of the comments there, just before I post this video, I started off originally as a cabinet maker, I think 25 years ago now. So I was doing cabinet making, and then that was fine. Then I went on to got a computer, got contacts with the whole world, which was amazing, as you know. And I started making casting patterns for people. Now at the time, I had no CNC machinery, so I just used to lay out the patterns, in mahogany, like the as another guy said, like there's a Cosworth video on YouTube you should watch. It's where they went with the Cosworth V6 turbo back in, can't remember what year, 1980 maybe, I don't know, but it's old school. But that's where I started, back in that era of making patterns by hand with chisels, knives, marking out gauges, and you'd make the pattern, send them off. You'd send them off to the company, and that'd be fine. At the time, there was no 3D printers. CNC machining was very complicated to make patterns at the time because, first of all, you'd have to have your drawings going in there 100% accurate. There's a lot of, in terms of making patterns, there's a lot of knowledge with the pattern maker of how the patterns are done. You could be missing a lot of details, whereas now, it's ridiculous. I think back then, or back, would say in my day, there'd be one or two engineers involved. Even like the M3, the E30 M3 engine was developed, I think, by one guy in about 16 days. Now we've got about 800 engineers on one engine. Like, what are they all doing? But anyway, that's just moving on, I suppose. But I'm not, I wouldn't ever be part of that. If I was born 30 years ago, or if I was, working on research and development, which I do now, small teams, and has to be done quick, have to figure it out quick. That's where I'm at. But going back to the patterns, they were all, my patterns here were cut in mahogany first. You do cylinder head molds like this or like this. You'd machine them all out of just mahogany with drill bits, chisels, and even your core prints and all were carved, which would be like the port models here. So you'd have to make a core box for this port sand mold here, which would fit into the bottom part of the mold. It would have to fit in tight. Now on the drawing, which thankfully were metric at the time, but sometimes they're imperial, you might have a 1-inch core print for this core would have to go into the sand mold, and even making a 1-inch divot for the dowel to fit into. It was all done by hand, so it was a big job. But there was various ways of doing it without CNC machines. Hand saws, chisels, even like I have one here, I have an old one here. You're all familiar with this. Let's just let me look on the camera to see. Yeah. This is a spade bit which you can buy in a shop. I'm sure you've all seen them, those that are carpenters or doing DIY. This is a 24mm spade bit. So what you can do with a spade bit, again, pattern making and casting is all kind of a black art. It's not really. It's just because there's so few people doing it. There's probably a few more now, but like back even 10 years ago, I think I knew about 4 guys that were over ginormous casting, what would I call it, offices or divisions in companies. And they were still very old school. They were all about 65, 70, and they're probably, some of them I know are dead. So I don't know what the companies did after that, but the one thing that was common with casting, which is totally off topic, but you could go into a shop and buy these. Obviously the big thing in a machinist shop was to keep the sawdust to the minimum. So you could machine out a pocket, in a mahogany part with a router bit or a milling machine bit or whatever you like with XY interpolation. But the problem with that is it made a huge amount of very fine sawdust. So probably the next day on the same machine you were doing all these patterns on, you had to actually run the parts on when they came back from the foundry. So it was in your interest to keep the shavings to a minimum. So this drill bit, these bits are spade bits, as I said, or flat bits. I don't know what you call them stateside or in the Western world, but this is what we call them here. They just drill in like that. They keep fairly concentric, and away they go, and they make big shavings which are easy to clean up. So if you were running coolant the next day on the machine, you could clean all the shavings off the machine pretty easily without cleaning fine dust, which a small, like if you were to go in there with a 6mm or a 1/4 inch milling machine bit with an interpolation on a rotary axis, you'd have huge amounts of fine sawdust all over the machine, which would get into the ways, which would block them. It would get into the coolant, and it would be just a disaster in the evening to clean up. So I used to buy these bits, or the pattern makers like worldwide, I know for sure in the United Kingdom would buy them, and you could actually tune them, which is a nice tip. And again, totally off topic, we'll get to this in a moment, but it's very important, I think. So if you want to bore a hole, if you go down to your local hardware store tomorrow, you want to do a job the weekend in the house, they only have got 24mm bits, and you need to drill a 27mm hole for fitting a lock on a door or a handle or whatever you want, making a birdhouse. You can buy these bits, and what you can do is you can cut them down there with a hacksaw. Alright, and when you have that cut made, you can then tap in a chisel here or a screwdriver or whatever you want, and you can spread out the wing here, and you can actually tune the bit to whatever diameter you want. So you can go, like this is 24, I think this is cutting a 28mm hole, 28.25, so you can go very accurately if you just bend out that sawed wing. And obviously for less accurate jobs you can bend it in again. Now it's only going to take a few. This bit I think has been bent, actually sometimes they crack. This bit has been bent, I'd say about, I don't know, probably 20 times doing different core prints. So that's a nice tip for anyone that wants a bit bigger than 24mm, if that's all you can get, or if you have one in the shop 19 and you want to go 3/4, you can bend it out 0.05. But yeah, hacksaw cut, drive in your screwdriver or chisel, bend it out a bit, and you've got a perfect diameter hole. So that's actually, there's a crack there, would you believe? It's been bent so many times. Yeah, that bit could tell a tale. So also if you got a 24, you can cut it down there with a grinder, and you can cut it down the other side to make a smaller hole and start off again. So buy your bits about 40mm diameter, and you'll have them for years. Anyway, that's a tangent. So getting back to modern methods, as we call it. Now this was still made. This is the water jacket gallery of the Brian Hart head. Now they're more or less the same in all engines. You know, you have to cool engines, it has to go around the valves. This would have been made at that time in wood, carved out in wood, made in a core box. You can actually see the parting line there, made in a core box like this. So top half, bottom half. The box will be carved out painstakingly with chisels, or maybe a CNC machine, but I don't think so, looking at it. I mean, this is different to here, and this is a bit weird looking here. So I would say it was done by hand in 1996. So they would make the core box, and it would be two cavities coming together like this. You can see the parting line, and you close the core box, blow in the sand, probably maybe here. Sand would be poured in here, and the sand would set. You'd open the core box, and you'd have your sand mold. All right. Now, where is this going? The advancements in engine technology and casting, especially over the last 50, I always have to check the date, like, because I think, you know, 2010 was like 5 years ago, but in the last 15, 20 years, this has come on a huge amount. And it's because of a patent, which is what these are here. So with the sand mold, it has to be fairly, like this is sand, keep in mind. So you have to be able to put it into the mold and it not break. When the metal comes in, it has to be able to keep supported, not break. If it does break, it's going to fall down. This is going to go like this. You're not going to have coolant here, or you're going to have the sand touching the top of the combustion chamber here, and you'll have no coolant flow, and it's going to be a disaster. Or it'll go this way, break, and wash out. You can even see the paint cracking there, where it wants to break, you know. So these are all the thin areas, and again, you've got a huge amount of sand here, because you have to have it strong and able to place it down in the mold and it not break. So this is where it has come on a huge amount in the last 15 years, because in, I think, 2009, a company called, what was it called? It was called, I think it was called Southwest Institute, or Southwest Research and Design Institute, came up with a process where you could keep all the big sections in sand, okay, which would remain strong, and you could do the very small sections. If you wanted to go down really thin, you could do them in a very fine ceramic, which would be like a aluminium powder and a very fine, probably zircon sand mix with an organic binder, which might be what was it called? It'll be the anhydrous version of silica gel, which is called, it won't come to me, sodium silicate. So that was mixed with that, so you can make a really fine, like almost a tablet which you take if you were sick, like a, I don't know, for head colds. It would resemble that fine powder, could be really dense. You'd make it by mixing up a solution, like you'd mix plaster Paris. If you've ever done, you know, models of plaster Paris with your kids or when you were young, you'd pour it into a rubber mold, you'd take off the rubber mold, and it'd be a very fine detailed little insert core, which would then fit into this main sand core. Like, you'd keep the normal sand core for the big areas, but for the small fine areas where you wanted water to go, or where you wanted fine details, or there not to be too much aluminium, you'd use a very fine plaster Paris, let's call it, impression mold, which would fit in there, which could be super high resolution, super small little ways, and be very strong, so it wouldn't break. Like, again, just going back to the sand mold for a moment, this is a sand mold here. Let's not put it on those because we'll need those in a minute. This is a sand mold here. Let's just see, can I see? Yeah, perfect. So this is a sand mold here. Nowadays, you can actually take your CAD design and you can send it off to the company and get it 3D printed in sand. My God. So that put pattern makers pretty much out of business overnight, except the very good ones. But this mold was sent to me by a company in Germany, which I won't name because they're not sponsoring the channel. They've never given me anything. I just did it as a favour because they wanted to see. This is a printed mold, as I said. They wanted to see how the mold would ship. Now there's a part missing here, which is the name on it, which I'm not going to show because I'm not going down that route. So they wanted to see how the mold would ship over whatever distance it is from Germany to Ireland, and just to see how it would ship, how it would like they were all stacked together. This is the core here, so this would be the core, as it would be, like if you can imagine this smaller, the core would be the core that would form the valve ports. There'd be 4, and the exhaust ports there'd be 2 more there, but this was the core of the part. So this would fit in here like this, not like that, like this. And your aluminium then would pour in here down the down sprue, and obviously the shape of your part then would have about a 7mm wall and fill up the part. But just to go back to how delicate these are, so I have one here. Now the binder that they use, this is just normal sand. It's it varies on grit. If you want to do a very complicated casting, the grit is larger so that the air will travel. Excuse the hands, by the way, I've done a lot of work this evening on this video, which you'll see in a minute. But on a complicated casting, the grit is a lot more. It's a lot bigger. It's like, I can't remember exactly, probably 180 grit. Because if you've got a complicated casting, there's a lot of flow, there's a lot of turbulence, the air has to go through it, so the grit is bigger. If you've got a smaller casting, you can use finer sand because there isn't as much air to be displaced out of the casting. So this is what it looks like. It's just a piece I broke off the other one. So that's it as it is sintered. Now again, this is 3D printed. A machine puts down a layer of sand, normally 0.02 or 0.2 millimeters high, puts down a layer, lasers down. The layer of sand is mixed with I don't want to say a formaldehyde binder, let's just say a phenolic binder, and once the laser light hits this, it cures the binder between the sand grains and it fuses them together. Now here the sand would still be in the machine, but the laser doesn't bind that, so when this part is printed, this sand can come out because it's all loose. It's not bound together, it's not fused together. But this is the finished item. Now if you eat biscuits, now I don't know what biscuits are around the world, but in Ireland we've got digestive biscuits, which are like a biscuit you dunk in tea. That's kind of what it resembles when it's fused together. Now the thing with this is, I think we can put this, no, I won't put that away for a minute, I'll just leave this soaking. The thing with the binder and this sand is, when the mold is finished or when the part is poured, you put it into water, not to cool it, but to dissolve the sand. So water will break down the bind or the binding agent between the particles, which will then let you flush out the sand. Both from the outside, you can smash off a lot of this or it'll come off, but an inner core, like if that was an inner core of sand, you need to wash out all this out of the cylinder head. So it's important that this is easy to dissolve, which was a big thing in 3D printing, because it needed to be flushed out easily, because you know you could have a huge area there left that didn't flush out, and number one, that wouldn't get cooled there if it wasn't flushed out, and number two, if it did start moving when you were machining it or when the engine was running, all this would end up in your water pump. So you don't want sand in your water pump. So if I just put this into water for 1 second and leave it there, can I see that? Yeah, you'll see what happens. How are we on time? Fine. So this mold was shipped to me, as I said. Now I think in the end, I'm not 100% sure what happened. I think they set up a foundry themselves because they discovered that after shipping parts to the States, and I think they shipped them to Singapore as well, they discovered that the parts change geometry a fair bit when they were being shipped, depending on how, like, you can't control how a box is put into a van. So if it was put into a van this way, it would have been fine. But if you put it into a van this way and have the cope on top of it, the cope is always vibrating on the top, so it changes the geometry of the part, which you'll see here, hopefully, with the calipers. I'll just bring it up actually. Hopefully you'll see it. So you can see the erosion in the sand there when it was being shipped. So the cope sat here, and it also sat there, but the cope was sitting a bit harder on the outer edge. So it just basically eroded away, like the sea on the beach, as you can see there. Like it's like a biscuit. So I'm not sure if the business idea worked out for them in terms of shipping parts or shipping just molds. Again, you can see the top parting line here. It's well eroded. All right. So that was their test. That's why I got it. I think it was the first part that was poured in the EU, possibly from a 3D printed part that was shipped. It was poured here. So that was pretty cool. But that's enough of it. Is there anything else on that to mention? This is while we're here, and the videos are always a bit of a ramble. So this is the core. The aluminium would pour all the way around that and surround it. This core would form the inner part, like if you can imagine it as like a glass or a vase. This would form the inner shape, stop the metal going in there. So this vent here, when the aluminium comes around this part, obviously it's very hot. There is air in this part. The air expands. If it has nowhere to go, which is here, the air will expand, boil, and rupture the thin wall of this let's call it a glass. So that's why there's a hole there. So the hot air can come out here, out of all the sand. Remember, it's pores, so there is air there. Comes out here, comes up here. If I bring back the parent mold again, so that hole vents the hot air out here, up to the top, and away safely, and doesn't ruin the casting. So this wall stays intact, and all these features. So if we just flip it around here for a minute. So this is the top of the mold. Now at the time they weren't too sure how to do the tops, but this is the vent from the core, as mentioned here. Comes up here, up to atmosphere. This I think was just to save sand in the part, because they're hugely expensive. I think they were retailing these parts at approximately €400 to get those printed, which would be a fair amount. So anytime the printer isn't printing, they're saving money, they can print something else. So here is where the metal would flow. You put in your filter here, which is like a Brillo pad, or like a pad for cleaning saucepans. So it'll be like, I don't know, stainless steel swarf, but that's what it'll resemble, but it's actually ceramic. It's a ceramic foam filter covered in I think it's a zircon wash, which goes in there and filters out any particles. Like if you're casting cylinder heads or high performance stuff, and if you're using virgin ingots, that's fine. Say LM25, which would be a common thing for high performance heads, or stateside it'd be A365. That's fine. But if you're using some remelt, which would be gates of other parts, or old cylinder heads, old gearboxes, which are totally fine to use, you can have a team stripping them, which are the best team in the world, but sometimes they will miss a ball bearing, which you've seen in the previous videos, where there has been a drilling into the casting, and they've put in a ball bearing and swaged it to block off a drilling. You don't want that ball bearing ending up in your crucible and ending up in your part. So that's why you put in a filter there. Now, at the time when I got this part, I wasn't that awfully happy with the gating arrangement. because you would need obviously you can't just pour into the filter directly. You'd need another mold nearly as high on top to direct the metal into the filter and all that. But they were very early company at the time starting off, so you know, that's just a minor detail, but that is the way it's gone. Send off your file, you'll get your mold back printed. And I think they will do a simulation as well on the mold flow solidification, which doesn't look to be too well done on this part, but that's what these parts are for, which we'll get in a second. So I'll set them aside, stop the video, because it's on what, 30 minutes and a half. It just makes it easier to upload in sections. Alrighty, so we're back. Just as I was taking a break there, I saw one comment on YouTube. It's hilarious. Some people what they've for doing or for nothing for doing. That he looked at one of the videos and he said this knowledge is rubbish. You know, it's useless. So one time I would have been offended by that, but 15 years writing on the internet about you know, technical stuff, I just laugh at them and just delete the comments. So any ridiculous comments, they're gone. Don't even bother. But getting back to the sand molds, so this has been soaking for about 4 minutes, 5 minutes, and as you can see, it's a lot easier break now. So that just washes out compared to something that hasn't been exposed to water is quite hard. So you leave once your casting is done, you leave it soaking in water, and it'll flush out easy. You can see the grains there, it's already starting to dissolve. So if you left that for, you know, 12 hours, it'll just all wash out. So that's that. Now, getting on to what the video was actually about 40 minutes later. So the older cylinder heads were just done this way. You know, you needed robust cores, like it'd look like this. You needed robust sand cores to be able to put them in, to be able to handle them without them breaking. And with the result of that is you need a huge amount of aluminium here. You can see how strong this needs to be. On the intake side, they didn't bother with a bridge at all because the valves were so big. They're bigger than the intake side, as you know. The valves were so big they couldn't put a little thin core down on here because it'd be just too fragile and it'd risk breaking. As I said, like if you just deflect this a small bit, I know this is silicone rubber, but sand would just break like a sand castle. It'll break a lot easier. So that would just break off. With the result of that piece there in the middle could break off and it could, you know, end up anywhere and block an important coolant way, which might be between the exhausts. So in, as I said, 2009, a company called I can never think of the name of it, Southwest Research Institute came up with an idea where you could use a large sand mold, normal for the big parts, and put in a very small, like really tiny, that size part in the middle. You could bond a small ceramic high definition part into the middle of it, which resulted in them being able to form very thin coolant ways here, 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 and also mean that you hadn't got a huge mass of aluminium, which, as you know, when you pour aluminium, the more dense or the thicker sections cool last. So for example here, there was a huge risk in this part. I would imagine they scrapped a lot of these parts. So if we look at what area here, that will show on the camera, yeah, here. So you've got really thin area here of aluminium, and like this is, you have to think in the negative now, and down a small bit. Now don't go too much into trying to think about this, but let's just describe it on this part here because it's easier, you can see it. But it's all in the negative and out from this part. But if you had a very small thin section of aluminium here and a huge thick section, which would be the spark plug boss, the thin sections which would be around the ports, you know, the port walls, which would be about 4 millimeters thick, they would cool first, obviously, because they're less dense, there's less thermal energy in there. So they would cool first, and this huge mass then of aluminium, which would be left around the spark plug, would cool last, which was a huge issue because that would then result in, as this is solidifying, this would solidify first, the thin wall of the port, and this would solidify last. So as this is cooling, it's shrinking more and trying to pull aluminium from the already solidified part, which would cause a little tear here in the aluminium, which would then obviously let the coolant, you know, in here and out into the exhaust, into the intake port and into your engine. So that would be a failed head long before it got to the CNC machine. Now, if I put this on here, this video is going to be way longer than I thought, but it doesn't matter. It's all good. So if I put that on here, again, it's getting fairly worse for wear now, this model. You can see where the aluminium wall of the port would be here. Just let me have a glance on the camera. Let's bring it up. So you can see the aluminium port would be here, be about 4 mil thick or 5 mil thick. Now this has been ported, so it'd be a small bit thicker. There'd be 1.5 or 2 mil left on it for machining. So that's really thin here. Yet you'd have a huge mass of aluminium here that they needed for the spark plug boss. And again, if I just remove it off a small bit, just to show you, exaggerate it, you'd have a huge amount of aluminium here and all the way around here on the deck face, which would also solidify last and be sucking aluminium from this solidified zone, which will cause cracking. So with the new idea that they came up with, that company I mentioned a minute ago, which I won't mention again because I can never think of it, Southwest Research, they devised a method of making a really thin core, as mentioned. Now this had two effects. It got rid of the huge mass of aluminium here, which they had to have because they couldn't make the core so small, it'd be so fragile. So that resulted in a reduction of tearing, hot tearing it's called, where one metal solidifies for the other. Hot tearing issues were reduced, and they could also then make these areas a lot smaller here, which meant they could support the combustion chamber more. Like, you have to keep in mind, on this side the piston is pushing up here, so all this combustion chamber had to be supported well with aluminium in the proper places, but also had to flow coolant through those areas. So what you want is maximum support, minimum amount of material, aluminium, LM25, and it not looking like this. It looking like a far thinner structure. So if I bring back the two prototypes that I made this evening, which are these, which originally started my talk on the pattern material which I used to use. I don't do much patterns anymore because I've just gone beyond that or moved on from that. But with mahogany, it was very cheap, or it's not called mahogany anymore because it's now protected. Brazilian mahogany was what initially was used for patterns, but nowadays it's called sapele. I think it's environmentally friendly, forest mahogany, wood, whatever. It's like mahogany, but if you buy something now that's called mahogany, it's not. It's sapele. But it was cheap. You could buy a plank of it for like a 12 by 4 plank for about 90 quid. Whereas moving on, this is epoxy tooling board. It's really high density. I think from memory it's about 900 kgs per ton. So it's quite dense. It machines well, and this is the new pattern making material because it's environmentally friendly, supposedly, and it's also suitable for carbon fiber parts, which I do a lot of. It can go into an autoclave. It doesn't outgas. You can paint it. It's safe. It can be sanded. Blah blah blah. So here we have two models. So with these models, they're not done exactly correct. Obviously they're a lot smaller. If you look at this, they're about 3/4 scale, and again, don't think too much about what these look like. Just keep in mind that these areas here are where the aluminium goes. Now, going back to another video, which was the half the point of this video, is I want to show you now the method I devised a long time ago on how to gauge aluminium solidification in a complicated casting without spending, I think it was €21,000 at the time, on solidification software. So if you're on a budget, the next part is for you. Again, not the point of the video, but more so the point in how technology has advanced. You can get more cooling around the spark plug. You're not left with a huge mass of aluminium here where the coolant can't go around. You can run higher compression ratio because you've got more support above the combustion chamber, and you've got more cooling, so you have no hot spots. Now that last 5 seconds was very important. So the method I devised was, so if you imagine this is where the aluminium goes, so that's your intake ports. These are both the same in principle. So your intake ports, exhaust ports, intake, exhaust, spark plug, spark plug. Old method, new method, which that company came up with, Southwest Research Institute, yeah, in 2019-ish. So it was gigantic at the time. They won, I think, several awards. It was, I think, the top 100 innovations in the last 50 years probably, and it's only very new, so it's worth mentioning. It never gets mentioned, and it is the absolute reason why you could make more power from Formula 1 engines or any engine. So what I'm going to do now is I'm going to show you my method of how I came up with an easy way to display solidification. Take that in a video because it's going to take a second or two and you're just going to have to wait, and then finish the video with why their patent or their method made such a difference. So again, we're gone way over time, but who cares? It's all good. So what I'm going to do now is I'm going to clean off that first. These are machined here. I machined these on the CNC earlier. I have a machine in house here. It's a CNC machine I developed myself for just testing different drives for different, ball screws, spindles. It makes other CNC machines, so it's a pretty accurate machine. But I did this here about an hour ago. Just machined into this model board, and hence the hands. But what I'm going to do is mix up resin here, which I discovered a long time ago from making pattern cores, which is a resin I don't mind mentioning. It's called Easy Flow 60. Some of you will be very familiar with it, I'm sure, that make models or work in R&D departments. It's a polyurethane casting resin. Now the fantastic thing about this resin, which I only copped on to about 12 years ago, is that you mix both parts together and it's completely clear when it's mixed. It's an exothermic reaction, which means that when the two are combined, they give off heat when they react together, and as they cure, they turn white, which is the major thing. So I'll mix them up, pour them in. It cures in about, I think, 3 minutes, so I should have enough time to explain what's going on while they're curing so you can see it live. Now it's important to note that you might want to go back and pause it when I do start doing this, because this resin, when it starts to go off, it literally cures like that. So it's going to go white quite quickly, literally before your eyes. But I'll talk you through what's going on and why it relates to aluminium casting while it's happening. So I'll stop the video, talk in a sec. Okay, so I got the resin poured. Now remember the old-fashioned method is on the the left, and the new method is on the right, which is the patent Southwest Research method. Now, at the time, they worked with Granger and Worrell, which is the company in the UK that does all the Cosworth F1 casting. So, I mean, they knew they were onto a good thing in the early days when they came up with the patent pending. Now, keep an eye on this because I mightn't be able to as I'm talking, but hopefully it doesn't go off too soon. It's looking all right yet. Again, this is epoxy tooling board because it doesn't suck any heat out of the reaction, so it should be exactly as it should be when it's solidifying if it was aluminium. But as it starts to, it's a slow enough process because once it goes in the areas of most mass, I'll be able to talk you through it, but it's not going to happen that quick, but it will happen within the next 2 minutes. So if I just show you this casting here again, which is the scavenge manifold, again, keep an eye on these. Actually, it's happening now. So as you can see here on the left, the white area here, it's solidifying. The resin is. Now, the white area here would be the last one to solidify if it was aluminium. So you can imagine this area here is all solidified already. This one has just started. This is all solidified, and it's now, this is now trying to pull frozen aluminium into this as this big mass solidifies. So that's where the issue was. You can see there's a vast difference in this one. It's a lot smaller. This one again, this is still molten here if it was aluminium. So these are all solidified, 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 and this is trying to pull aluminium here. So you would get a tear. Let's just get this out. You would possibly get tears in these areas here where this has gone hard, this has gone hard, this has gone hard, and this has gone hard. So this by now is gone way down in temperature if it was aluminium. It's well solidified by now, or sorry, it's well, these are well solidified, this is still molten. So you can see where the possible issues would be here, 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 and here, and here, and here, which would let in water into the exhaust and intake ports, which you can see if we move to the new method. This one is a lot more gradual. It's solidified a lot, what would I call it, a lot, how will I put this, this is where it gets confusing. It's solidified more uniform, let's say. So these are all solidifying now, much the same time as this, because it's much the same mass, and this one is still, this has probably got, yeah, this has gone hard by now. You can see that, while these are still soft. Okay, so if you imagine this the reverse, if it was aluminium, this is hard, or sorry, this is hard, yeah, sorry, this is hard, this is soft. So it takes a bit of thinking just to get into your head. It's probably not the most easiest way to demonstrate it, but if you're doing prototype castings, as I said, it's just magic, you know. So again, like these are already gone hard here, this has gone hard, while these are soft. So it's the reverse if it was aluminium, and we'll just leave it there for a sec, and we'll talk about this part again. So these were the company that in the UK that company that patented that process worked with, GW, which you can see it on the part somewhere, Granger and Worrell, yeah, which is here, it's just been machined off. GW, that's their logo. So they were working with that company at the time, which developed the process to make this area a lot smaller here and make the solidification a lot more uniform, or happen at the same time, besides this one here, which is a huge mass, which has already gone hard. you know, which is the opposite. If it was aluminium, this would be still soft. But we'll see at the end of the video which one solidifies first, which one doesn't, and we can take it from there. It'll be easier to explain. But this is a GW part, Granger Moral. They're well used to making castings, as you can see. Just leave the inside for a second. I don't want to dip the part into them. So I mean, fairly complex, this part. Core, there's a lot of cores here. You know, cores here from the various scavenger manifolds. Now I will cover this part again in the next series of videos or whenever. Yeah, nice part. Again, machined here. This was probably machined here because, why was that machined there? Oh yeah, because the machinist needed to get access. He had to machine this off first here to get access to machine this bore here. So you can see there, he would have to got his tooling in there, down there, and machine that. So that's what, about 300 millimeters of a boring bar. So that would have been fun. Yeah. So with the bar that length, if you're machining a tight bore, if you measure the boring bar diameter at the top when the machine is off, when the CNC machine is off, or the VMC, the boring bar can measure bang on. Let's just say that's what, let's measure it. Let's call it 17 millimeters. So if you set your boring bar to 17 millimeters up here and you turn on the machine, because the bar is so long, the centrifugal or centrifugal, depending on where you're from, forces can cause the bar to splay out like that. So even if your bar is 17 millimeters here, once you turn on the machine, go down, bore your diameter, because the bar is spinning and trying to fly out this way, the bore can be oversized. So there's a lot of things to think of if you're a machinist. But yeah, nice part. Which again, I'll go through all this oiling system in the next video, with scavenge systems, with crankshaft oiling, all that sort of thing, and we'll have a good look at that. But back to the molds again. Let's see how they're behaving. So again, you can see the one with the huge mass in the middle, which would have been, they're both actually going off now. So you got the main point at the start of the curing process, but you can see how a huge mass is detrimental to, you know, like the casting could fail very easily if you've got a huge mass of material here. Like, it's not that consistent. You can see these are still soft here, which means if this was aluminium, they would have solidified first. This would be last. So this is still molten. These are still solidifying. So this is all in risk of a hot tear area here, and with the exhaust ports. Now, if we just so that you know, it's that way. I know you know, but there's a big mass here. So I would say they scrapped a lot of these heads because of that reason. There's just a huge amount of aluminium here. Now, if you look at the modern methods, which I'll put in a picture probably now, hopefully I can find a non-copyrighted image of the part. I should be able to. I think it's open source, so I should be able to insert a video or an image now of the new core method. You can see this one has all solidified, so it's all hard. So the more uniform mass, due to the smaller core here in the middle, due to the ability to be able to cast the small core finer in a finer powder, as said, and still be resilient for handling. That's a major breakthrough in modern Formula 1 engines, that you can handle the core, put it in, it's not going to move, and It's more precise, more supports the combustion chamber, and major. So that's hopefully presents all that theory of the core advancements here around the spark plug area, whereas the old method here, which is, it's probably gone hard now. No, it's not. It's still, so you can see it's still soft. So again, if this was aluminium, this would be still soft. This would be solidified a long time ago. So it's a nice method to be able to test how your molds are without simulation. You know, you can do it very easily with that resin. It's called Easy Flow 60. Just again, it's a polyurethane 2-pack exothermic resin, and the brilliant thing is when you pour it, it's clear. When it starts to cure, it turns white. So in time, I don't know how many videos down the line, I will do a video on the CosCast process, which is a patented Cosworth casting process which they do internally, which will explain this even more. But hopefully that video, which was way longer than I thought, should give you a bit of an insight on how they made more power with the newer engines than the older engines. More mass here, higher risk of casting failure, less cooling around the ports, less combustion chamber support, because if you do want to do that, you have to provide more cooling. New method, far more uniform cooling, more support, less material, less tearing issues. That's episode 10. Hard to believe, again, once again, episode 10 gone already. Jesus, it's flying. So keep subscribing. Up there, there's new parts. I added them this evening if you want to buy new parts, which featured in the previous videos. And if you don't want to do that, buy me coffee. If you don't do that, subscribe. If you don't do that, sit back, relax, and just look at the videos. Have a good one. Talk soon.